Hello, I'm going to go over this worksheet, Evidence for Curved Spacetime. Now we're dealing with two pretty challenging ideas, at least to really kind of get into your head. The first one is spacetime, and that space and time are actually one thing. They're not separate. So we have spacetime, which came about from Einstein and relativity. And then we have to think about space-time as being able to curve or warp. So I'm going to go through some of the evidence for this, but this has been studied extensively, backed up with every single experiment that we've tried on it. So this is fact. This isn't just hypothesis. But let's take a look. So what I have down here is a model showing the sun. And go ahead and copy down the notes that I'm filling in here. So we've got the sun here, and in this case, we've got Mercury. So we started to look at the orbit of Mercury for evidence of curved spacetime. And what we noticed is Mercury does not follow the rules that Isaac Newton laid out for physics. These are our classic rules of physics, the physics that work for us in everyday life for building any of our big structures or engineering or anything like that. So Mercury did not move as predicted. When it goes around the sun, because of this curved space-time, because of the gravity actually bending space, Mercury as it orbits kind of follows this weird path because it's dipping into and out of that extreme curve closest to the sun. And what happens is, if this is our sun and this is Mercury, what we see is this really weird orbit. Now I'm going to exaggerate this, where Mercury goes around and then it kind of loops this way and then loops this way. And the only way we can explain that is from a curved space-time. So that's one, the orbit of Mercury. Another piece of evidence is something called gravitational lensing. And there's lots of good images of gravitational lensing online, but from an observer, here's Earth, an observer on Earth, if we're looking at a couple of galaxies here, we have one galaxy in the middle, and then we have another galaxy behind it. These are in line, right? And what happens is, it's not just planets and stars that have enough gravity to distort space-time, but whole galaxies can distort space-time. So they're curving space-time, and the light from this galaxy behind actually gets bent as it goes past. Oops, let's take that back just a little bit. And it can get bent around all sides of this middle galaxy. And what we see, the weird thing is, since the light is being bent, and the light is going in a straight line, it's just that the straight line is a curved space line. Since the light gets bent, we actually see images of two or maybe more of these galaxies. So what you'll see here is one galaxy, and then you'll also see the same galaxy, but they're just on opposite sides of this particular galaxy in the middle. That is gravitational lensing, where we see multiple images of one object. All right, let's try a few more here. Another experiment that we did with the Viking satellites, I believe this was in the 70s, I want to say. But in the 70s, what we set up was we had Earth on one side, this Viking satellite on the other side of the sun. And because, again, the sun is curving space-time, we had the Vikings send us radio signals. Very simple radio signals coming from the satellite back to Earth. Okay. What happened was, we knew the exact distance between these, but because of curved space-time, the radio signals had to go just a little bit further, and there was a time delay. And this time delay can only be explained through curved spacetime. And it had to be set up where Viking was on the opposite side of the sun from where Earth was. All right, there's also another thing called gravitational redshift, which we can see. We know what wavelengths should be coming out of certain stars. But what happens is, because the space around the star is so curved, we get what's called gravitational redshift, where the light, which travels in waves, the waves start off really close together, and then they get further and further apart. So gravitational redshift. And what that means is this light that we're observing is more red than it should be. And again, it's because of the curved space-time close to the sun here. All right, the last little thing, and this is about gravity waves. So we've been able to detect gravitational waves. Very difficult to do, very difficult. We built this huge lab for it, which is like 4 kilometers long in each direction. It's got these really long straight lines because we send in a series of lasers bouncing off mirrors in both of these directions. And when we get a gravitational wave that comes through here, it actually distorts space as it moves, as the wave moves through this facility. And all it has to do is distort space just a teensy tiny little bit, and the lasers will be unaligned. And when I mean teensy tiny, I mean teensy tiny. I mean 1/10,000th the diameter of a proton. That is unbelievably small. I don't even know how to give you an idea of how tiny that is. But just that little bit of distortion from these gravity waves caused the lasers to be out of sync, just a tiny little bit. And that was only recently. We've only been doing this for maybe the last 6 or 7 years. All right, well, I hope this helps at least a little bit. It's a hard concept. Don't worry if you don't fully get it yet.